Hello class, this is Fire Service Hydraulics and Water Supply, Chapter 13, Determining Pump Discharge Pressure. We're going to go through several learning objectives, and I'll start with number 1. Learning objective 1 states the basic formula for calculating pump discharge pressure. Number 2 demonstrates how to calculate pump discharge pressure in simple hose layouts. Learning objective 3 demonstrates how to calculate pump discharge pressure in complex hose layouts. In addition to understanding and calculating pressure losses, the driver operator must also understand the concepts of pump discharge pressure and net pump discharge pressure and their relation to nozzle pressure. Pump discharge pressure at the apparatus must be able to overcome the sum of all pressure losses. These pressure losses, combined with required nozzle pressure, are used to determine pump discharge pressure. So for calculating pump discharge, we have equation 13.1, which is PDP equals NP plus TPL, given that PDP is the pump discharge pressure in PSI, NP is the nozzle pressure in PSI, and TPL is total pressure loss in PSI, which is appliance, friction, and elevation losses. All nozzles are designed for optimum operations at particular nozzle discharge pressures. In general, these pressures are solid stream handline nozzles, which are 50 psi, solid stream master stream nozzles, which are 80 psi, low pressure fog nozzles, which are 70 psi or manufacturer's recommendation, and standard fog nozzles, which are 100 psi or handlines and master streams. If a pumper is supplying a hose line is also supplying another pumper, then the desired intake pressure at the pumper being supplied should replace nozzle pressure in the equation. The pumper supplying multiple hose lines, wide hose lines, or manifold hose lines will likely have to provide different pump discharge pressures for each attack line. Because the pump can be set to only one overall pump discharge pressure, the pump operator must use another method to compensate for individual pressure requirements. When this occurs, the operator must set pump discharge pressure for a hose line with the greatest pressure demand. If multiple hose lines are attached to the pump, the operator must gate back the valves for the remaining hose lines at the discharge outlets using individual discharge pressure gauges as a guide. If the pump is supplying wide or manifold hose lines that have different attack line pressures, the operator should use a ball valve on the appliance to get back hose lines until obtaining a desired pressure on each line. Unless the appliance has individual pressure gauges on each discharge, adjusting lower demand attack lines will depend on trial and error. Some review questions. Which two factors are added together to get the pump discharge pressure? See page 387 in your manual for the answer. Next question. If the hose line being supplied by the pumper is being used to supply another pumper instead of a nozzle, what happens to nozzle pressure when calculating the pump discharge pressure? That is on page 388 in your manual. Learning objective 2. Demonstrate how to calculate pump discharge pressure in simple hose layouts. The vast majority of firefighting situations require a single hand line or two or more individual hose lines. Calculating required pump discharge pressure for these situations is not particularly complex. The first step is to determine the total amount of pressure loss in hose lay. The second step is identify the required nozzle pressure for the nozzle or nozzles being used, and then use equation 13.1 to determine the required pump discharge pressure. Let's use example 13.1 from the book. Determine the required pump discharge pressure to supply a 200-foot, 1-inch booster line at ground level. The line is equipped with a 30 gallon per minute fog nozzle. Step 1 is to determine the total pressure loss. So to do that, we use our old friend, the formula FL equals CQ squared L, and then we plug in the numbers. Friction loss equals 15.5, which is the coefficient from our table. 30 divided by 100, that's your hose length, divided by 100 squared, times 200 divided by 100, which is the additional hose length squared. And then we take friction loss equals 150 times 0.30 squared times 2, and we work out the math to 150 times 0.09 times 2, and the friction loss comes out to 27 psi. Step 2 will be determine the nozzle pressure. The nozzle pressure for a handline fog stream is 100 psi. So step 3, determine the pump discharge pressure. So you have PDP, which is pump discharge pressure, equals nozzle pressure plus total pressure loss. So PDP equals 100 plus 27, so your PDP is 127 psi. Determine the amount of pump discharge pressure to supply a 100-foot, 1.5-inch pre-connected trash line at ground level. This line is equipped with a 95 gallon per minute fog nozzle. This is example 13.2 from your book. Step 1 is to determine the total pressure loss. So we have our old friend, the formula FL equals CQ squared L. The next step is to plug in numbers. So we have friction loss equals 24 times 95 divided by 100 squared times 100 divided by 100 times friction loss equals 24 times 95 divided by 100 squared times 100 divided by 100. So when we work out the math, we have friction loss equals 24 times 0.95 squared times 1. And continuing the math, we have friction loss equals 24 times 0.9025 times 1. So it comes out to friction loss equals 21.66 or 22 psi. So let's look at example 13.2. In step 2, determining the nozzle pressure. The nozzle pressure for a handline fog stream nozzle is 100 psi. So we already know this. So step 3 is to determine the pump discharge pressure. So to do that, we take PDP, pump discharge pressure, equals nozzle pressure times total pressure loss. So PDP equals 100 plus 22. So PDP is 122 psi. Many departments replace booster reels on their apparatus with short pre-connected 1.5-inch or larger hose lines to handle small jobs. These lines require lower pump discharge pressure than booster line while providing more than 3 times the volume of water. In almost every firefighting situation, more water volume is desirable. Here's an example to look at. This is 13.3 from your book. A pumper is supplying 2 pre-connected attack lines at a small dwelling fire. One line is a 150-foot, 1.5-inch hose equipped with a 125 gallon per minute fog nozzle. The other line is a 200-foot, 1 3/4-inch hose line equipped with an automatic nozzle flowing at 150 gallons per minute. To determine the required pump discharge pressure for this pumper. So we're going to determine the total pressure loss in each line from our example on the previous slide. So our friction loss for the 1.5 inch hose equals CQ squared L. You should be very familiar with that formula by now. So we'll plug in the math. The friction loss for the 1.5 inch hose equals 24, which is our coefficient, times 125 divided by 100 squared times 150 divided by 100. And when you work out the math on the next line for the 1.5 inch hose is 24 times 1.25 squared times 1.5. That calculates out in the next line to 24 times 1.5625 times 1.5. So the friction loss for the 1.5 inch hose is 56.25 or 56 psi. So our friction loss for the 1 3/4 inch will be the same formula, CQ squared L. So friction loss on our 1 3/4 inch is 15.5 times 150 divided by 100 squared times 200 divided by 100. And that gives us on the next line 15.5 times 1.5 squared times 2. And that calculates out to 15.5 times 2.25 times 2. And that calculates out to friction loss in 1 3/4 inch hose as 69.75 or 68 psi. Okay, let's look at some simple hose layouts. This is example 13.3 from your book. Step 2, determine the nozzle pressures. The nozzle pressure for both handline fog stream nozzles is 100 psi. So step 3 will be to determine the pump discharge pressure for each line. So if we look at the left, that's one line. So the PDP, pump discharge pressure for the 1.5 inch line, is the nozzle pressure plus the total pressure loss. So we add in our numbers. PDP for 1.5 is 100 plus 56. So the PDP for the 1.5 inch line is 156 psi. If we look at the right hand side, that's our PDP for the 1 3/4 inch line. So it's PDP equals nozzle pressure plus total pressure loss. So that's PDP at 1 3/4. We plug in the numbers, 100 plus 68. So our PDP is 168 psi. The pump discharge pressure must be set for the higher of the two lines, which in this case is the 1 3/4 inch hose line at 168 psi. So let's look at an example. This is example 13.4 from your book. A pumper is supplying multiple hand lines to attack a commercial fire. This is figure 13.1 on page 392 of your text. One discharge is supplying 150 feet of 2.5 inch hose that is wide into two 1.5 inch attack lines, each 100 feet long and flowing 100 gallons per minute through an automatic fog nozzle. The second discharge is equipped with 200 feet of 3 inch hose with 2.5 inch couplings that is supplying a handline solid stream nozzle with a 1 3/8 inch tip. Determine the required pump discharge pressure for this pumper. So what we see here is the diagram of the pumper. We see two lines. One is 150 feet of 2.5 inch hose. The other is 200 feet of 3 inch hose. On the 150 feet of 2 inch hose, we see a Y that's splitting into two lines, each of 150 feet and at 1.5 inch hose, and they're producing a discharge of 100 gallons per minute each. The other hose is 200 feet of 3 inch hose, and it has a 1 3/8 inch tip at 50 psi. So let's determine the pressure loss in each line. For the wide lines, we've got friction loss for 1.5 inch line equals CQ squared L. There's our old friend, that formula. So the friction loss for 1.5 is, once we plug in the numbers, 24 times 100 over 100 squared times 100 over 100. That gives us a friction loss on the 1.5 inch line of 24 times 1 squared, or 1 to the second power, times 1. So if we work out the math, we get the friction loss for the 1.5 inch hose at 24 times 1 times 1. So it gives us a friction loss on the 1.5 inch of 24 psi. If we look at the friction loss for the 2.5 inch, we get friction loss at 2.5 equals CQ total, because that's your total number of gallons flowing, squared, plus length. So we have friction loss at 2.5, and we plug in the numbers. 2, which is our coefficient, times 100 plus 100 over 100 squared, times 150 over 100. That gives us a friction loss on the 2.5 of 2 times 200 over 100 squared, plus, or times 1.5, and we work out the math. The friction loss for 2.5 is 2 times 2 squared times 1.5, and if we extrapolate the math, we end up with friction loss on 2.5 of 2 times 4 times 1.5. That gives us a friction loss on the 2.5 inch line of 12 psi. So determine the total pressure loss in each line. Total pressure loss of the wide line equals the friction loss of the 1.5 plus the friction loss of the 2.5. So the total pressure loss in the wide line is 24 plus 12. So the total pressure loss in the wide line is 36 psi. Note, an appliance loss is not applicable because the flow is less than 350 gallons per minute. Step 1. Determine the total pressure loss in each line. For the 3-inch attack line, you have gallons per minute at 29.7, that's your coefficient, times the diameter squared times the square root of nozzle pressure. And let's just plug in the math. So we have gallons per minute equals 29.7 times 1.375 squared times the square root of 50. That gives us gallons per minute of 29.7 times 1.89 times 7.07, and that calculates out to gallons per minute at 397 gallons per minute. Now let's look at the friction loss in the 3-inch line. So if friction loss in the 3-inch line equals CQ squared L, there's our formula. So friction loss for the 3-inch line is 0.8, our coefficient, times 397 over 100, that's our length, divided by 100 squared, times 200 over 100, that's our length, divided by 100. So we have friction loss for the 3-inch line, when we add in the math, at 0.8 times 3.97 squared times 2, and when we extrapolate all the math, we have friction loss for the 3-inch hose at 0.8 times 15.76 times 2. So our friction loss for the 3-inch hose is 25.2, which is 25 psi. Step 2. Determine the nozzle pressures. The nozzle pressure for the wide line, hand line, fog stream nozzles is 100 psi. The nozzle pressure for the 3-inch hand line solid stream nozzle hose is 50 psi. Step 3. Determine the pump discharge pressure for each line. For a PDP wide line, you have nozzle pressure plus total pressure loss wide lines. The PDP wide lines equals 100 plus 36, so your PDP wide lines is 136 psi. Now, you have PDP3 is nozzle pressure plus total pressure loss times 3. PDP3 equals 50 plus 25, so PDP3 is 75 psi. The pump discharge pressure must be set for the higher of the two lines, which in this case are the wide lines at 136 psi. Some review questions. What is the first step in calculating the required pump discharge pressure of a single hand line or two or more individual hose lines? See page 33 of your manual. Why might a department choose to shorten a pre-connected hose line instead of a booster line? Please see page 390 of your text. In Learning Objective 3, we're going to demonstrate how to calculate pump discharge pressure in a complex hose layout. Pump discharge pressure for complex hose layouts must be determined methodically. It's similar to determining total pressure loss. Here's one example. A pumper is supplying multiple hand lines to attack a commercial fire. This is on figure 13.2 on page 395 of your text. One discharge is supplying 200 feet of 3-inch hose that is wide into two attack lines. One attack line is 150 feet of 1.5-inch hose equipped with a 95 gallon per minute fog nozzle. This line is deployed to the roof of a 20-foot building for exposure protection. The other attack line connected to the Y is 200 feet of 2-inch hose equipped with 200 gallons per minute fog nozzle. The pumper is also supplying two 3-inch hoses equipped with 2.5-inch couplings, each 300 feet long, and supplying a portable master stream device with a 1 3/4-inch solid stream tip. Determine the required pump discharge pressure. This is a layout of exactly what they just described. You got your pumper with 200 feet of 3-inch hose. There's a Y separation. Off of that, you have 150 feet of 1.5-inch hose on a 20-foot roof at 95 gallons per minute. Then you have a 200-foot hose at 2-inch hose, and it's discharging 200 gallons per minute. And then off the pumper, you have both hoses that are 300 feet of 3-inch hose with 2.5-inch couplings feeding a portable master stream nozzle. And it's a 1 3/4 solid stream nozzle. So let's determine the pressure loss in each line. For the wide lines, the friction loss for the 1.5-inch line is CQ squared L, our regular formula. So the friction loss for the 1.5-inch line is 24, we're plugging in the numbers, 24 times 95 over 100 squared times 130 over 100 squared. So the friction loss for 1.5 is 24 times 0.9025 times 1.5. So it gives a friction loss on the 1.5-inch line of 32.49 or 32 psi. Now you have to look at the elevation pressure. Elevation pressure at 1.5-inch hose line is 0.5 psi foot per head. So the elevation pressure at 1.5-inch is 0.5 psi foot per head times 20 feet. So if you take 20 feet times 0.5, your elevation pressure is 10 psi. Looking on the right hand side, you have total pressure loss of 1.5-inch equals friction loss for the 1.5-inch line plus elevation pressure at 1.5-inch. So your total pressure loss for 1.5-inch equals 32 plus 10. So your total pressure loss for 1.5-inch line is 42 psi. Determine the total pressure loss in each line. Here's our formula. FL2, friction loss for two lines, equals CQ squared L. So friction loss for two lines is 8 times 200 over 100 squared times 2. So friction loss for two lines is 8 times 2 squared times 2. So the friction loss for 2 is 8 times 4 times 2. So the friction loss for 2 is 64 psi. Note, since there's no elevation change, this is also the total pressure loss for this line. Now we have to determine the total pressure loss in each line for the wide lines. So we have friction loss for line 3 equals C times Q total, which is the total amount flowing squared, times the length. So we have friction loss for 3 equals 0.8 times 95 plus 200 divided by 100, that's hard to see, times 100 over 100, or 110 over 100, excuse me. The next line, we plug in the numbers. Friction loss for 3 is 0.8 times 295 divided by 100 squared divided by 205 divided by 100. So the next line, we have friction loss 3 is 0.8 times 2.95 squared times 2. The friction loss 3 is 0.8 times 8.7 times 2. So the friction loss for 3 is 13.9 or 14 psi. I apologize, the copy's not real good on this slide. You can double check my math and double check the book. Now step 1, determining the total pressure loss in each line for the wide lines. The greater pressure loss in the two attack lines is the 2-inch line, so that figure is used to determine the total pressure loss in the wide line assembly. The total pressure loss of the wide line equals the friction loss of 3 plus the friction loss of 2. So the total pressure loss of the wide line is 14 plus 64. So the total pressure loss of the wide line is 78 psi. Note, the appliance loss is not applicable because the flow is less than 350 pounds per square inch. Now let's look at step 1. Determine the total pressure loss in each line for the portable master stream device. Our formula is gallons per minute equals 29.7, which is our coefficient from your chart that you should be familiar with by now, times the diameter squared times the square root of nozzle pressure. You should also be familiar with this equation by now. Gallons per minute, once we plug in the values, is 29.7 times 1.75 squared times the square root of 80. When you work out the math, you get 29.7 times 3.0625 times 8.94. So the gallons per minute is 814 gallons per minute. Now, if you want to look at friction loss for dual 3-inch lines, use the same familiar formula. Friction loss equals CQ squared L. You're just looking for dual 3-inch lines. So if you move to the next line, the friction loss for dual 3-inch lines is 0.2 times 314 over 100 squared times 300 divided by 100. Next line is friction loss for dual 3-inch lines, and that is 0.2 times 8.14 squared times 3. And if you continue the math, you get friction loss for dual 3-inch lines of 0.2 times 66.3 times 3. And the friction loss for dual 3-inch lines is 39.76 or 40 psi. You should absolutely be getting the hang of this by now. Step 2, determine the nozzle pressure. The nozzle pressure for the wide line, hand line, fog stream nozzles is 100 psi. The nozzle pressure for the master stream solid stream nozzle hose is 80 psi. Step 3 is to determine the pump discharge pressure for each line. The PDP wide lines equal nozzle pressure plus total pressure loss of the wide lines. So PDP of the wide lines is 100 plus 78. So PDP for the wide lines is 178 psi, of course. The PDP for the dual 3-inch lines equals the nozzle pressure plus the total pressure loss for 3. So the PDP for the dual 3-inch lines is 80 plus 40. So the PDP for the dual 3-inch lines comes out to 120 psi. The pump discharge pressure must be set for the higher of the two lines, which in this case are the wide lines at 178 psi. Supplying an aerial master stream devices is among the pump operator's most critical functions. If an incident has evolved to the point where controlling a fire requires an aerial master stream, then a large fire must be contained as quickly as possible to avoid potential conflagration. The pump operator needs to know the operational limits of aerial master stream nozzles and water supply system in order to avoid supplying too much pressure to the nozzle. It is crucial that a pump operator who must supply an aerial master stream device be given all pertinent information before charging hose lines. This includes the type of aerial device being supplied, the type of nozzle and its height, the length of the hose lay, and if any of these factors change during the operation, the pump operator should be notified immediately. In example 13.7, a large capacity industrial fire brigade aerial master stream device is protecting exposures at a large fire. The fixed waterway on this device is equipped with a 3,000 gallon per minute fog nozzle that is elevated 90 feet. A 3,000 gallon per minute industrial pumper will supply this device with dual 6-inch hoses, each 500 feet long. Determine the pump discharge pressure for this pumper. This is example 3.7 in your book. Step 1 would be to determine the total pressure loss. Since no coefficient for dual 6-inch hoses is available, assume that each hose is supplying 1/2 of the total water supply, or 1,500 gallons per minute. Then calculate the pressure loss in one of the hoses. Remember that the rule of thumb for pressure loss in aerial fixed device waterway systems is 25 psi. So we're still talking about aerial master streams. So let's look at example 13.7 again from your book. Step 1, determining total pressure loss. The friction loss on the 6-inch diameter hose is CQ squared L. Same formula. So friction loss for 6 is 0.05, which is your coefficient from the table, times 1,500 over 100, because you're running 1,500 feet of hose, divided by 100 squared, times 500 divided by 100. That's your second hose. So you have FL6 equals, once you plug in the numbers, 0.05 times 15 squared times 5. So FL6 is 0.05 times 225 times 5. So FL6 equals 56.25 or 56 psi. Now, in this case, you're running elevation pressure. So you have, let's look at the right side. Elevation pressure is 0.5 psi times feet times the head, pressure on the head. So you've got elevation pressure, which is 0.5 psi times 90 feet pressing at the head. So 90 divided by or times 0.5 is 45 psi. So your elevation pressure is 45 psi. So let's look at the bottom. You've got total pressure loss times friction loss plus elevation pressure plus appliance loss. That gives you total pressure loss equals 56 plus 45 plus 25. So your total pressure loss comes out to 126 psi. Step 2, determine the nozzle pressure. The nozzle pressure for an Ariel Master Stream fog nozzle is 100 psi. Step 3, determine the pump discharge pressure. That's easy. PDP equals nozzle pressure plus total pressure loss. PDP equals, in this case, 100 plus 126. So your PDP, or your pump discharge pressure, is 226 psi. Now let's look at example 13.8. Determine the pump discharge pressure in the hose assembly when a fire department pumper is supplying two 3-inch hose lines with 2.5-inch couplings, each 200 feet long. These hoses are connected to a Siamese appliance that is in turn supplying 100 feet of 3-inch hose with 3-inch couplings attached to a detachable ladder pipe. The ladder pipe is elevated 60 feet and is discharging through a 1.5-inch diameter solid stream nozzle at 80 psi. This is figure 13.4, page 400 in your book. So this is your actual setup. You have your pumper with two lines feeding into a Siamese unit that feed into a single line of 100 feet 3-inch hose with 3-inch couplings, and they are being fed up the quint to a master stream nozzle, and that's elevated at 60 feet. So we're still talking about Ariel master streams. So, and this is example 13.8 still. So let's look at determining total pressure loss. You have gallons per minute equals 29.7 times the diameter squared times the square root of nozzle pressure. Same formula we've been using. So we plug in the numbers. Gallons per minute is 29.7, that's your coefficient, and that's constant, times 1.5 squared times the square root of 80, and that gives us 29.7 times 2.25 squared times 8.94. So our gallons per minute is 598 gallons per minute flowing. If you look to the right, you see elevation pressure. Elevation pressure is 0.5 psi times foot of head. So the elevation pressure in this case is 0.5 psi foot of head times 60. 60 times 0.5 is 30 psi. Now if we look at the bottom, we have friction loss for dual 3-inch lines, and that is friction loss equals CQ squared L, same familiar formula. So let's plug in the numbers. Friction loss for the dual 3-inch is 0.2 times 598 over 100 squared times 200 over 100. So friction loss for dual 3-inch is 0.2 times 5.98 squared times 2, and when we work out the math, we get friction loss for the dual 3-inch at 0.2 times 35.76 times 2, which is friction loss of 14.3, which rounds down to 14 pounds per square inch. Now let's look at determining total pressure loss. Friction loss for the 3-inch equals CQ squared L, again our familiar formula. So we have friction loss for the 3-inch equals 0.677, that's our coefficient, times 598 divided by 100 squared times 100 divided by 100. So friction loss for the 3-inch is 0.677 times 5.98 squared times 1. So friction loss for the 3-inch is 0.677 times 35.76 times 1. So our friction loss for the 3-inch is 24.2 or 24 psi. Now, let's look at total pressure loss equals friction loss for the dual 3-inch plus friction loss for the 3-inch plus the elevation pressure plus the appliance loss through the Siamese plus the appliance loss through the nozzle. When you take all those numbers, which sounds like a lot, but you add them together, you get total pressure loss equals 14 plus 24 plus 30 plus 10 plus 25. So your total pressure loss ends up being 103 psi. Step 2, determine the nozzle pressure. The nozzle pressure for an aerial solid stream nozzle is 80 psi. Step 3, determine the pump discharge pressure. Pump discharge pressure is nozzle pressure plus total pressure loss. So your PDP is 80 plus 103. So your pump discharge pressure is 183 psi. Virtually all water pumps in use today are centrifugal pumps. This can take advantage of water pressure coming into the pump, and the amount of pressure in the pump is actually creating is the net pump discharge pressure, NPDP. The net pump discharge pressure takes into account all factors that contribute to the amount of work that the pump must do to produce a fire stream. Knowing the net pump discharge pressure is not a particularly important from a technical standpoint, but knowing its concepts may aid in the pump operator in critical flow situations. When the pumper is receiving water from a pressurized source, use the following formula. NPDP PPS equals PDP minus intake reading. Given that NPDP PPS is the net pump discharge pressure from a positive pressure source, and PDP is the pump discharge pressure in PSI. So let's take an example, 13-10 in your book. A pumper operating from a hydrant that is discharging water at 140 psi. The incoming pressure from the hydrant registers 50 psi on the intake gauge. Determine the net pump discharge pressure. So we have NPDP PPS equals PDP minus your intake reading. That gives you NPDP PPS equals 140 psi minus 50 psi. So your total answer is, or final answer is, NPDP PPS is 90 psi. That's your net pump discharge pressure from a positive pressure source. Intake pressure correction must take into account friction loss in intake hose and the height of lift. These allowances are then used in a formula to calculate pressure correction. Okay, let's talk about equation 13.3. This is for pressure correction. Pressure correction equals lift plus total intake friction loss divided by 2.3. This is table 13.1. This is the allowances for friction loss in intake hose. Like all charts, you'll become familiar with it. So definitely take a look at it. It gives you the rated capacity of the pumper in gallons per minute, diameter of intake hose. For 10 feet of intake hose, it allows for that, and it has an allowance in feet for each additional 10 feet of intake hose. This is the second part of that table, and this gives you the rated capacity of the pumper in gallons per minute, and again the diameter of intake hose, and for 10-foot intake hose, and allowance for each 10 feet of intake hose. Now let's talk about correction that can then be used to calculate net pump discharge pressure at draft. This is from equation 13.4 in your book. NPDP draft equals PDP plus intake pressure correction, given that NPDP draft is the net pump discharge pressure at draft and PDP is the pump discharge pressure in PSI. So here's an example. An 1,000-gallon pumper operating from draft is discharging water at 120 psi. The required lift is 9 feet through 20 feet of 5-inch intake hose. Calculate the net pump discharge pressure. So if we take our formula, pressure correction equals lift plus total intake friction loss over 2.3, and we plug in the numbers, we have pressure correction equals 9 plus 4.5 plus 1.5 divided by 2.3. So when we do all the math, we come out with pressure correction of 15 over 2.3. And when we divide that out, our intake pressure correction is 6.5, which you round up to 7 psi. So our NPDP draft equals PDP plus intake pressure correction. So our NPDP draft is 120 psi plus 7 psi. So our total NPDP draft is 127 psi net pump discharge pressure at draft. A couple of review questions for you. 1. What is one reason why supplying an aerial master stream is among the pump operator's most critical functions? See page 397 for details. The next question. List 3 pieces of information that the pump operator supplying an aerial master stream device must know before charging the hose line or hose lines. See page 397 for details in your text. Next question. What causes the net pump discharge pressure to be more than what is shown on the discharge gauge when at draft? That is on page 404 of your manual. Class, as always, we covered a lot of material. If you have any questions, please make sure to contact your instructor. Thank you for your time and attention. We'll meet again for Chapter 14.